there will be no change in the direction. So what's going to happen? This normal vector can't move, because imagine that if I move it from this point to this point, the direction would change. The direction would change. So if I want that this normal vector, okay, has a same direction as, not precisely same direction, but is behaving in the same manner, the same orientation actually, as what do you call this normal vector, then like this normal vector shouldn't move actually. And if so a normal vector, a transformed normal vector is not changing actually. Okay? Transformed normal vector is not changing. What does it mean? That the original space in which you are moving your normal vector is a flat space actually.
Sir, suppose this is a manifold here. At any point, you will get a point on the sphere, right? At any other point, you will get other points on the sphere. Now calculate the normal vectors, you would have the same direction, but there you would have different directions on the sphere. Because you have different points on the sphere.
And the whole entire is making on a single point.
Okay, I can see this trouble. See, in order to know the curvature, we are not interested in only the normal vector. We are interested in the change in the normal vector. So my point is that when I am moving normal vector here, there is no change in the normal vector. Okay, so I can have a point which can have a fixed direction actually. So when I'll move that point vector and move it, is not going to change anything here. So what I want to do roughly is that I want to estimate the curvature of the surface by moving a normal on it, and analogously, somehow they are interconnected with each other. Okay, by moving the what do you call normal on sphere. Okay, so I want to have an estimate for the curvature. Okay. So all these are approaches. There are several tricks and techniques basically that people have developed actually. But this one is beautiful. Think about it now. Imagine now you have a cylinder now. Okay? You have this cylinder. Now if you have a cylinder, you're going to have two principal directions. One direction is this. Okay? So imagine you have this page. Okay? And you kind of wrapped it. When you wrapped it and you joined it, obviously topologically the space has changed, but I can see this cylinder as a quotient of a, what do you call, a plane actually. And by quotient I mean glue the points, glue the ends. So what kind of curve I'm going to have? So I'm going to get some few straight lines, and I'm going to get some curves actually. So this is going to be okay. And now I'm saying that okay, let's take one of these horizontal lines on the surface, vertical lines on the surface. Okay, and let's draw a normal on it. Okay, so how does the normal would look like? It would be outward normal line. Okay, and if I'm moving this normal up and down, would there be a change in the direction? The normal vector would stay same. Okay. But how about this one? So if I'm taking a point and drawing a normal vector, okay, what's going to happen? So it is going to change, but it's going to change in a constant manner. Think about it. So if you have a circle, okay, and you have a tangent on it, and you have a normal on it, okay, and this, if you are putting this tangent into the motion, the normal will also be in motion, but this motion is going to be constant actually. Are you getting that point? So what kind of behavior are you going to get on the sphere? So that would be like on a sphere, you have a small circle, okay? You have a circle on which this normal vector is turning around actually. Wouldn't that be the case?
How? Sphere
sphere blur, take a small patch of circle, okay, and I'm saying that when the normal is moving on this circle, okay, changing the direction in one particular way, you know, on sphere the normal is also going to change in one particular way. So in other words, if I take, for example, if I do this experiment, if I take two principal directions, the two principal curves on the surface, and I see, you know, the variation of normal of it on it. So on one it is constant, you know, it's just fixed actually, but in other direction it is moving in a particular way, like moving on circle. Then I'm gonna have that, okay, this is what, this is like a cylinder actually. Are you getting the point? And I can play this game with any, what do you call it, so that was the one approach actually. Not making it rigorous. I mean, if there will be time, I can make it more rigorous actually. Okay, otherwise, I can suggest some resources where you have been taught in a very particular way in this, on all this actually. Okay, but that's the rough idea. What is the other way? What do you call the local way to deal with it? The local way to deal with it is this. But still it's going to be extrinsic. Okay. Before getting into it, at least I want to get some intuitive idea about something called the geodesics. So what's geodesics? Imagine we have this plane. Okay. And I know that on plane I can, so it's part of 2 dimension. What is the best way to reach from one point to another point? So if I take 2 arbitrary points, okay, and I want to compute the distance between them, so I can reach from point A to point B, for example, in a variety of ways. How many ways are there? I can draw a line, I can go through curve, and so on and so forth. Are you getting the point? So I would say this is the shortest possible path that joins what is called those 2 points. Okay. Now if I take the same plane and I transform it into a surface, what would be that point? I have the same points, for example. It can't be a straight line. The straight line here, so obviously, what I'm saying is that, okay, take this picture and, twist it, or maybe, give it a curvature. Okay, curve it. So this is going to be the line of the
Always curved over.
always curved. Okay, if you have a curved space, it is going to be always curved. And that curve that allows you to reach from one point to another point on the surface is basically called geodesics. That's geodesics. Okay. So by geodesics, we mean the shortest possible path to reach from one point to another point. For example, the geodesics on plane are straight lines. The geodesics on, for example, surface is basically this. So that's an abstract surface. But for example, if I take a sphere, okay. So by the way, what is such a representation, okay, of the sphere? So you have these, roughly circles, great circles actually, going around all. picture, you should have other car charts, but you can see that what I'm talking about. Okay. So if on a sphere, we are living on a sphere. Okay. So imagine, this is Karachi, and maybe I want to reach somewhere in New York. Not going to be like that about here at the North Pole, but okay, let's assume that. Okay. Then how can I reach from here to here? Okay. The best way to reach from here to here is to take the great circle. In other words, take the great circle that passes through these two points. Okay. So that would be the geodesic circle. So I can go this manner. So here's the thing. So take this surface, and I have 2 points, and I want to reach from here to there. I can have many lines that joins these 2 points. But what I have to do is that we always have to try to find the shortest possible path to reach from one point to it. So on sphere, what you call these great circles are the ways to reach from one point to another point in the shortest possible manner. And why we want to do it, why airlines want to take this great circle path, not the other path, because they want to save the fuel, they want to make the money. Okay, if you're going to take any other path, it's going to take time and fuel and everything, so it's going to be a troublemaking thing actually. So the geodesics basically on sphere are some kind of circles actually. Okay, and that's what is also a kind of a that's what is also going to be a kind of an important property that okay, if you have a manifold, what are the geodesics on that manifold? If you have a sphere, what are the geodesics on that sphere? We also going to learn. Basically, what you have to do, you have to solve a set of nonlinear differential equations, and you solve them, and you get the solution, and the solution gives you the curves actually. In the traces of the curves.
ये कह सकते हैं अगर n+1 का manifold ले तो n का हमारे पास manifold होगा geodesic.
Then manifold geodesics are going to be curves actually.
Always curves.
They are always curves. They are always curves.
For surfaces.
For surfaces.
But if you have something
Okay. So if you have a hypersurface, then yes,
n+1
it could be something, crazy. Is it making sense? But at the moment, we're restricting ourselves with the geodesics. Now, here's the thing. If you are okay, are we happy with the geodesics? If you are moving roughly on the principal direction, if you are happy with the geodesics, let me get now into the real stuff that I want to do actually. Then I'll talk about, because now I have some sketch of geodesic in my hand. So when I'll use the word geodesic, you will have some idea that what I'm talking about. So let's get into this stuff so that we can. Let's get into this stuff very precisely. Okay. So what I want to do. Shall I give you another illustration? One illustration. Okay. It's like the more pictorially you understand things, the more equations are going to make sense to you. That what the heck these things? Otherwise, these are abstract bunch of equations written in tensorial form. You have no idea what you are talking about. Okay. So the better is imagine this is a road in which you are kind of driving. That's a road. Okay. That's it. So you can assume it that okay, maybe you are going on valley. Okay. And going on top and maybe go to the what do you call north of Pakistan, maybe somewhere. So you always find some kind of crazy places actually. Okay. Go to Naran Tawan, you want to go to Safil Maluk for example. You have to pass through very crazy paths actually. Okay. Anyway, so it's this kind of form in which the half of your wheel is almost in the air actually. Anyway. So imagine this. Imagine I'm moving in this manner. When I'm moving in this manner, how the tangent is going to move with me. So that's a tangent here at this point. And at this point, so if I take a next point and draw a tangent, it's going to be here in this manner. Okay? Now if I take these two tangent vectors, okay, take these two tangent vectors, so take this tangent vector and say this other, so I'm interested in measuring how the direction of the tangent vector is changing actually. Take this vector and the other vector, okay, then this is the direction in the change vector, okay, or this is the direction of the normal, okay. How does the normal would look like here, okay, for this part of it here, this part is going to be inward, okay. So the more changing you are having, the more change in the direction of the normal is going to take place. So take a tangent vector, draw it here. You know, the normal is going to radically shift the, what do you call, the direction actually. Are you getting the point? Alright. So how do you get the change in normal? By studying the change in what do you call the tangent vector. Okay. So in this, when you are moving on this path, the normal is always going to change the direction. If you're going to reach here, it's going to be here, it's going to be, okay, here, and, you know, so on and so forth. You can sketch roughly the normal is when you are moving on this. So you can also treat this as that, okay, take a three-dimensional plane, okay, and just move it around the depth and see that, you know, how the normal is changed, like we did in the curve. But what is the best way to move on Earth? So if you want to move on Earth, in an efficient manner, then your path should be something like this. Maybe straight, but we know that it's not a straight, it's curved actually. And what will happen in this case? These are the tangential directions. Okay. What will happen to the normal? It's not going to change at all. Okay. It's not going to change at all. Okay. So when I am moving on this straight line, in other words, I'm moving on basically roughly a kind of a circular path, or in one of the principal directions, the normal is not going to change. In other words, here I can, okay.
The change होगा ना constant change.
Hoga constant, okay. But it's not going to be like basically. Okay, you can assume that okay, this is like up and down. Okay, it's like horizontal straight, you're going ahead, but it's up and down actually. Then yes, obviously it's going to be changed, but the direction still would stay same for the tangent and the normals as well. So my point is this: there are two things that you need to measure the curvature of the surface. You have to study or you have to kind of resolve your normal vector into basically two parts. Number one, if you are moving on geodesics or you are moving on some other than geodesics. If you are moving on a path which is some other than geodesic, then your normal vector is going to have two parts. Two parts actually. In other words, think about it. On this curve, if this curve is on a sphere, there are two things responsible for the curvature of this curve on sphere. Number one, the curve of the sphere itself, and the curve of the curve actually, the curvature of the curve. So there are two quantities which are responsible if you are moving on, what do you call, something other than geodesics. But if you are moving on geodesics, one of the, say for example, principal directions, okay, so the only thing that is responsible for the curvature is the curvature of the the surface actually. Is it making sense? The curvature of the surface. So think about it. So if I take this line, okay, and I curve it, then these lines are curved because the surface is curving. Are you getting the point? But if I take any other curve and I curve it, then I'll say that there is two kinds of curves, basically curvatures on this curve here, okay, that are responsible for the curve. The one is the curvature of the curve itself, and other is surface. And that's what basically, so these are the two basic quantities which are going to basically, that we have to study. One is called the normal curvature, the curvature due to the surface. Another is the geodesic curvature, basically, which essentially tells you that how your curve is differing from the geodesics. Okay? Things will get gradually clearer, but just want to give some realization so that we can see that what kind of things we are talking about. So let's get into, okay, I don't know, since almost last hour I'm talking about geometry, let's do something practical. So what I would like to talk about is, so imagine I have, I'm in UV plane dimension, and I have this part of the UV plane. It's not necessarily a rectangle, okay, it could be anything, okay, and I am transforming it, so taking the points of UV, this part, and I'm transforming it through some, what do you call, a map, okay, and then it's going to give me what? Give me surface, okay. So it's going to give me a surface, but in 3 dimensions. Okay. And how does the surface is going to look like? The surface is going to look like something like that. In other words, these principal lines, these lines actually, not principal lines are technical meaning, but these basic lines are going to turn now into the curves actually. Is it making sense? And then I'm saying that, okay, let's take a point here and take, say for example, the tangent vector xu in one of the principal direction and xv in the one of the other principal direction, and I'm going to get an outward normal, okay, that is going to be an actually. And I want to study this normal. Okay? And I want to say that, okay, how this normal would change on this surface. This is what is the key thing. So here is the basic notation that x is x of u alpha. Okay, so it's something that depends on u alpha. A patch on M. Okay, and xu and xv are tangent vectors. Okay, tangent vector, or maybe these are the tangential vectors to surface. Okay, the tangential vectors to surface. And then how can I compute this unit normal vector? You take the cross product of xu cross xv and compute the magnitude of xu cross xv. Okay, that's computed. And now assume that on this surface you have a curve actually. You have a curve passing through a point, or maybe a particular curve, for example. So let's take a curve. An arbitrary curve, not necessarily the curve in line with these basic curves, principal curves. Okay, so I have a curve. So let u beta, which is going to be u beta, let's call it u beta of f, okay, b, without loss of generality, I can assume that it's a regular curve, okay, with what do you call it? Which parameterization? Arc-length parameterization. Okay. Curve with parameterized by arc-length. Parameterized by arc-length. Okay. Now there are three things. So one is this ambient space, three-dimensional space, okay, and a surface and a curve actually. That is a curve on the surface, but these curves also have an existence in R3. So I can also see this as an independent entity in R3 actually. Okay, so this is also an important thing that I've learned. So just treat first this curve as a curve in R3. So if it is a curve in R3, I can have a Frenier frame here. Okay, I know that if you have a curve in space, you can have tangent normal and binormal vector on that basically. Okay, so let E be the tangent normal and binormal. Okay, the Frenier frame on the curve. Frenier frame on curve. Okay. We have to keep one thing in head, that this n is not necessarily same as this n. That's the normal of the surface, while this guy is a normal to the curve, so it could be in any direction. Okay, but one thing that is shared is going to be the tangent vector. So if I take a point on a curve, okay, if I take a point on a curve and draw, for example, a tangent vector, maybe I take a point here and draw a tangent vector to it. Now this tangent vector, which is a tangent vector to the curve, is also tangential to the surface. Okay, are you getting the point? Okay. So how does this? Okay. So let me write it explicitly. Take a point, and I have a tangent on it, and a normal to it on it, and a binormal on it. Actually. So this is something extrinsic. Okay. As a curve, you are getting all this information. So if you have curve, then you can have this Frenier frame on the curve. Okay. Now we also proved something. Okay. We proved that if you compute the derivative of this Frenier frame d and t and b, okay, then I can write this as what? Remember? The vector t and b multiplied by a matrix vector. And what was that matrix? That matrix was 0 minus k ds, 0 k ds, 0 minus tau, okay, tau ds, okay, and 0 tau ds and 0. That is what do you call metric. Now the key point that I would like to make now is basically based on the approach of Darboux. The thing that I'm going to use is also called Darboux frame actually. So Darboux was a guy. There is also something called the Darboux way of doing integration. There's a pretty famous guy, Darboux, and We can also call it a Darboux-Cartan approach actually, because Cartan basically made the approach of Darboux more sensible and more practical actually. Okay. So what does this approach is saying? It's saying consider a new frame. Okay. And this frame is F.